So what is principle of virtual work? It says that if a particle or a rigid body or system of rigid bodies which is in equilibrium under various forces is given an arbitrary virtual displacement, then the net work done by the external forces during that displacement is zero. Okay, so a particle or a rigid body or a system of rigid bodies when they are in equilibrium, okay. So suppose if we are giving some virtual displacement, so because there is no actual displacement, that means the net work done by the external force during that displacement is zero. And this principle is particularly useful when applied to the solution of problems involving the equilibrium of machines or mechanism that consist of several connected members. Okay. And if a particle, rigid body or system of rigid bodies is in equilibrium, then the derivative of its potential energy with respect to the variable defining its position is zero. Okay. So now let us understand the work of a force. So suppose this is the force, okay, which is applied at point A, and suppose this particle under the action of this force moves to another point A dash, and these R is the initial position vector of the particle and R plus dr is the final position vector, while this dr is the displacement vector. Then the work of this force will be given as F dot dr, means dot product of the force and displacement, and which we can also write as du is equal to F ds cos alpha, as you already know how to open the dot product. Now there are some situations when the both force and displacement is in the same direction, that means alpha is equal to 0, then this work is simply equal to the product of F into ds. Okay, while if this alpha is equal to pi, that means the force and the displacement is in the opposite direction. That usually happens with the weight force, which is because of the gravity. So in that case the W work is du is equal to minus F dot ds. Okay, and if alpha is equal to pi by 2 means the force applied, okay, and displacement, they are perpendicular to each other, means they have the 90-degree angle. So as we know that cos 90 is 0, so that means the work is 0. So this is very important. Whenever the force and displacement they are perpendicular to each other, then the work done will be 0. Okay. So now we will discuss some important forces which do no work. So first one is the reaction at a frictionless pin due to a rotation of a body around the pin. Okay, so this force reaction at the frictionless pin will do no work because there is no lateral motion, only rotation is there. So this force will do no work. Second, reaction at a frictionless surface due to motion of a body along the surface. So because this is causing a perpendicular arrangement, okay, because reaction at the frictionless surface is always perpendicular, and suppose this is the body, okay, and body is moving in this direction, So we can say that this is angle is 90 degree. Okay. So whenever the force and displacement is 90 degree, then the work is zero. So in this case also the work is zero. Similarly, weight of a body with CG moving horizontally. So in this case also the weight which is act vertically downward while the center of gravity is moving horizontally. So again both the forces and displacement they are perpendicular to each other and there will be a no work. Then friction force on a wheel moving without slipping. So again in this case, suppose this is the wheel and it is moving without slipping. Okay. So the friction force will be always opposite to the motion, and this is the motion of the wheel. So they will always be perpendicular to each other. So again there will be no work. Okay. Again, sum of work done by several forces may be zero apart from these conditions when bodies are connected by a frictionless pin. So as in this case, these two bodies AC and BC they are connected by a frictionless pin. So there will be two forces F and minus F. So if this force is doing a positive work and then the work of this force is negative and both the works add up to zero. Okay. Similarly, body is connected by an inextensible cord as in this case. So again, suppose if this is doing positive work, so then this will do negative work, then both the work will be overall the work will be zero. Similarly, third case is internal forces holding together parts of a rigid body. So suppose this is the rigid body and these are the 2 points A and B and we are having forces F and minus F. So these are the internal forces. So again, if we see from the external, there is no force. So in this case also, the work of these forces, internal forces will be zero. Now let us see the work of a couple. Okay, so again consider the rigid body and suppose these are the 2 points F, A and B and the couple is acting on AB. So suppose this is F, this is minus F. So under the action of the couple, there are two type of motions: translation motion from AB to A dash B dash, okay, and rotation of B dash about A dash to B double dash, okay. So under the action of the couple, these two points A and B they move to A dash and B double dash, and we can divide it into two parts: translational motion plus rotational motion, okay. So now this the translational motion this will cancel out. So well, suppose we have minus f dot dr and plus f dot dr, so this will cancel out. And finally, the work which will remain is only f dot dr2, okay, which is nothing will but f ds2, which will be equals to f r d theta. So if this is the vector r, so this is the distance r and this is angle d theta, then r d theta will be equal to dr2 and f into r is nothing but the moment. So work from a couple we can say that will be equal to moment into the angular rotation of the body m d theta. So this is very simple. We can calculate the work of a couple by this expression w is equal to m d theta. Now what principle of virtual work says? So imagine a virtual displacement of particles which are acted upon by several forces. Suppose multiple forces are acting on the body. So the corresponding virtual work will be F1 dot delta R plus F2 dot delta R plus F3 dot delta R. So we will consider the work from every force and then we will add that. So we will get the total corresponding virtual work. So now this expression we can write like this. We can take delta del r dot as common, then the work will be F1 plus F2 plus F3 dot delta r, and we can write the resultant of this. So the work will be R dot delta R. Now there are some points related to principle of virtual work. First is, if a particle is in equilibrium, the total virtual work of forces acting on the particle is zero. Because the particle is in equilibrium, it is not moving, so that means the total virtual work should be zero. Okay. And if a rigid body is in equilibrium, the total virtual work of external forces acting on the body is zero for any virtual displacement of the body. So if any rigid body is in equilibrium, then what we will do, we will calculate the virtual work and then we will equate it to zero, and then we can calculate any unknown quantity. And the third point is, if a system of connected rigid bodies remain connected during the virtual displacement, only work of the external forces need to be considered. So if there is some displacement in a rigid body which is connected, there are several rigid bodies which are connected, so we will consider the displacement only because of the external forces. Now how we can apply the application this principle of virtual work. So suppose this is a body, and there are two rigid bodies actually, AC and BC, and suppose this P is the external force which is acting, and this is the initial angle between this line and the rigid body is theta. Now suppose under this force, this body deform in this shape, so that this angle, this change in angle is delta theta, and this vertical movement in the vertical direction is delta yc, and movement in this axial direction is delta xb. Okay, so under the action of this forces and these reaction forces, these are the movements. So now you can calculate the virtual work. So virtual work will be delta uq, okay, plus means because of the force p, plus delta up because of the force p. Okay, so these p force and q force, they will do work, and this is because this is the frictionless spin, so and the rotation motion is there, so these forces will do no work. Okay, now work because of the q will be under the action q, this is the displacement, and both are in the opposite direction, so this work is minus q delta xb, and again this work is p delta yc, because this yc is negative, so minus yc. Okay, now we can write the expressions for xb. So this xb is nothing but 2l sine theta, because this part up to this point, sorry, up to this point is l sine theta plus l sine theta. So this xb will be equal to 2l sine theta, and then we can differentiate it. Then delta x will be 2l cos theta delta theta. Similarly, you can write expression for yc. So yc is l cos theta. Then we can differentiate. Delta yc is minus l sine theta delta theta. So now we can put these expression in this equation. So final equation of delta work, virtual work is minus 2ql cos theta delta theta plus pl sine theta del theta, and from this we can get the expression q is equal to half of p tan theta. Okay, so if we know this value of p, then we can calculate q, or if we know q, we can calculate p. So this is how we can do the problems related to virtual work. So first of all, we will calculate the work of a force during a finite displacement. So as you already know that if a force is acting on any particle or a rigid body, and there is some small displacement dr, then the work is equal to F dot dr. This we already know, and we can write is F ds cos alpha. Okay. Now suppose this is your element. Okay. So suppose it is the initial position is this, and ds is the small distance through which this element moves because of the action of this force. Now work for a finite displacement from point A1. So this is the initial point A1, and this is the final point A2. Okay. So this work you can calculate by simply integrating this expression f ds cos alpha. So f cos alpha ds from S1 to S2. Okay. So by simply integrating, you can calculate the total work of which this force do on this particle when this particle moves from point A1 to point A2. And similarly, you can calculate the work for the couple. So if some couple is acting on any particle, and because of that couple there is some rotation d theta, then the work is du is equal to d theta, and for a finite rotation the work will be m integral of theta 1 to theta 2 d theta, and finally you will get m theta 2 minus theta. Now let us see the work of a force during finite displacement for some situations. So consider this first situation when your particle is either moving up or moving down. So this is called as work because of a weight. Okay. So we know the work is equal to because the small displacement is dy, then small work du is equal to minus w dy. And suppose this weight moves from point A1 to point A2, then the work during this finite displacement u12 will be integral of this w dy from minus y1 to y2, and this work is negative because both are in opposite direction, displacement and force. Now when you integrate it, you can get this equation wy1 minus wy2, and which is equal to minus w delta y. Okay. Similarly, suppose this is the spring, so work of a spring. So in the undeformed form, this is the undeformed form of the spring, and suppose it is deformed slightly to x1, and then spring force will also act in the opposite direction to this deformation, and suppose this is the final position. Okay, so we know that du is equal to minus f into dx because they are in the opposite direction. Now spring force, we know we can write spring force by this expression f is equal to kx. So in this expression of work we can write kx dx, and for this finite displacement we have x1 to x2, and when you integrate this then you will got half kx1 square minus half kx2 square. Okay, so this is the work from a spring, and this work can also be calculated with the help of this diagram. Okay, so suppose on the x-axis we have taken the displacement, on the y-axis we have taken the applied spring force, sorry. So then work can be calculated with the help of area under this curve. Okay, and this curve, this area will give you the work. So the shaded portion will give you the total work, which is nothing but minus 1 by 2 F1 plus F2 delta X. So this is how you can calculate the work of a force during a finite displacement for certain situations. Let us see about the concept of potential energy. So we know that the work of a weight we calculated just recently, that work is equal to Wy1 minus Wy2. So from the expression we can see that the work is independent of the path and depends only on the initial and final position. Okay, so we can also know, we also know that from our previous knowledge that this work into height, it is also known as the potential energy of the body. Okay, so we can see that the work is equal to simply the change in potential energy. So this one is the potential energy at first location, and this expression will give you the potential energy at the second location. So work through a finite displacement is also equal to the change in potential energy. Okay, similarly, the work of a spring, we know this expression, half kx1 square minus half kx2 square. Now this one is the potential energy of the spring at position 1, and this is the potential energy of the spring as position 2. So again we see that work of a spring through a finite displacement is equal to the change in potential energy of the body with respect to the elastic force. Okay, so this E represents the elastic, okay, and just and G represents the force of gravity. Now when the differential work of a force is given by an exact differential, okay, then we can write this expression, work is equal to the change in potential energy, negative of the change in potential energy, or work from point 1 to point 2 is equal to simply the change in potential energy between point 1 and point 2. And one more important point, forces for which the work can be calculated from a change in potential energy are conservative forces. So this point is very important. Those forces for which we can calculate the work by simply calculating the change in potential energy are called conservative forces. For example, our gravitational force, this is the conservative force, and our spring force. Spring force is also a conservative force. So spring force is also a conservative force. Now let us see the relationship between potential energy and equilibrium. Okay. Now suppose when the potential energy of a system is known, then the principle of virtual work will be like this. So as we all know that for the application of principle of virtual work, change in work will be, sorry, any work should be equal to 0, and we can also write it as minus delta V, because del U is minus delta V for the conservative forces, and we can write in this form also. So minus dV by d theta delta theta. So now for the potential energy and equilibrium we have this expression. Okay, and because it's delta U is equal to 0, so this thing should also be 0. Okay, so dV by d theta should be 0. Okay, so for the potential energy and equilibrium we have change in potential energy with respect to theta should be 0. Now so suppose for this structure we have potential energy, total potential energy of this structure is elastic potential energy plus gravitational potential energy, and now we know this elastic potential energy is half kx b square. Okay, and this gravitational potential energy is WYC. And XB, you can get the expression for XB, and then you can simply put, then you will get half K 2L sine theta square plus WL cos theta. Okay. Now for equilibrium, what we do, we differentiate this equation with respect to theta and put it equal to 0. So finally we will get this equation, L sine theta in bracket 4KL cos theta minus W is equal to 0. Okay. So we will get two answers, which shows that there are two positions of equilibrium for this body. Okay. So I think this is clear.